We tend to think of randomness as just pure chaos, unpredictable, messy, totally without rules. But what if I told you that even within that chaos, there are these deep, predictable patterns? Today, we're going to pull back the curtain and look at the mathematical laws that actually find order in all that randomness. So let's start with a situation we've all thought about. Picture it. You're watching a coin flip. It comes up heads. Okay. Then heads again. And then a third head in a row. At this point, your gut is probably screaming that the next one has to be tails, right? It just feels like it's due. Well, that feeling is super common, and it's also completely wrong.
Yeah, that flawed intuition, it actually has a name, and it's a mental trap that has fooled gamblers, investors, and pretty much all of us for centuries. So let's break down exactly what this mistake is.
This quote really gets to the heart of it. We have this really powerful, deep-seated belief that past random events somehow influence future ones. You see a long string of reds on the roulette wheel, and you just know black has to be next. Or maybe a stock goes up for 3 straight days, and you think it's due for a drop. And here it is. Its official name is the gambler's fallacy. It's this mistaken idea that some kind of short-term cosmic balance has to happen in a sequence of completely random, independent events. So what's really going on here? Well, the fallacy basically assumes that the coin has a memory, that it somehow knows it's been heads a few times and thinks, oh, I should probably be tails now. But in reality, each coin flip is a totally independent event. The odds are 50-50 on the first flip, the fifth flip, and the 500th flip. It doesn't matter what came before. That coin has no idea it's supposedly due for anything. Okay, so if our gut feeling about some law of averages is totally off, what's the real law that's actually at play here? Well, that brings us to the real mathematical principle that governs all of this, the law of large numbers. And this is where things start to get really cool. To put it simply, the law of large numbers says that over a very long run, things really do even out. As you flip a coin more and more and more times, the total percentage of heads will get closer and closer to that perfect 50% we expect. But the key words here, and this is really important, are large numbers. This is a long-term thing, not some kind of short-term fix. And here's the part that's a little counterintuitive. Let's say you start with a really weird streak, right? Like you see here. Maybe in the first 10 flips, you only get 40% heads. The universe doesn't try to correct this by forcing a bunch of extra tails later on. Not at all. Instead, that initial, small, weird streak just gets completely drowned out. It becomes totally insignificant when it's averaged in with thousands or millions of future flips that are all hovering right around that 50-50 mark. And believe me, this isn't just some abstract theory. It's the foundation of entire industries. Casinos literally build their empires on this law. They know that while one person might get lucky and win big tonight, over millions and millions of bets, the casino's small statistical edge guarantees they'll come out ahead. Insurance companies use it to set premiums, and pollsters rely on it to be confident that their small sample actually reflects the entire population. So, the law of large numbers tells us what the average is going to be over time. But what if we could predict something even more specific? Our next idea, the central limit theorem, is, well, it's almost magical in what it tells us about the actual shape of random data. Think about it like this. We know the average of a ton of coin flips will get closer and closer to 50%. But what if we did a whole bunch of experiments? Say we flip a coin 100 times and write down the average. Then we do it again, and we do this thousands of times. If we made a graph of all those different averages, what would that graph even look like? This right here is the central limit theorem. And it's honestly one of the most mind-blowing results in all of statistics. It says that if you take groups of samples from any set of data, and it doesn't matter how weirdly shaped that original data is, and you plot the average of each of those groups, the graph of those averages will always form a perfect bell curve. Just take a look at these two starting points. On the left, you've got a totally flat, uniform distribution where every outcome is equally likely. And on the right, you have this completely bizarre, lumpy, irregular mess. Intuitively, you'd think that samples taken from these would also look flat or lumpy, right? But check this out. This is the magic. By the time we're averaging just 4 little samples at a time, look what happens. The distribution of those averages is already starting to form that familiar, perfect, predictable bell curve. And this happens whether you start with the flat one, the crazy one, or almost any other distribution you can dream up.
It's a fundamental pattern just emerging out of the noise.
Okay, so what? It's a neat trick, but who cares about a bell curve? Well, this is the crucial point. If we know that random processes naturally produce this predictable shape, we can actually use it to make some incredibly powerful predictions. So let's try a practical question. If you flip a fair coin 40 times, what's the probability you'll end up with a result somewhere between 15 and 25 heads? Now, you could calculate this exactly, but it would be an absolute nightmare of calculations. So instead, we can use the central limit theorem as this amazing shortcut. We already know the results are going to form a bell curve. So all we have to do is first figure out the center of that curve, the average, which in this case would be 20 heads. Then we figure out how spread out the curve is. And once we have that shape, we can calculate the probability of landing in our target range, right between 15 and 25. The theorem lets us get a great answer without doing all the hard work. And the answer you get is about 91.8%. That's amazing, right? The central limit theorem allows us to take a really complex, messy probability problem and turn it into a surprisingly simple calculation. It literally finds the order in the chaos. So let's just quickly recap what we've covered. First, we busted the myth of the gambler's fallacy because random events don't have memories. Then we saw how the law of large numbers is the real principle at work, guaranteeing that things even out in the long run. And finally, we witnessed the magic of the central limit theorem, which shows how that beautiful bell curve is hiding inside almost any random process you can find. And this all brings us to a final, bigger thought. These mathematical tools, they allow us to find these profound, powerful, and really useful patterns in something as chaotic as a simple coin flip. So it kind of makes you wonder, doesn't it? If we can find this much order hiding in pure randomness, what other giant, complex systems in our world are just waiting for us to find the right patterns?